Hello, everyone. Today we're going to be looking at an overview of the entire mechanics syllabus, and I'm going to make this like an a kind of long video, but this is just a general overview of like let's say a revision guide, kinda. So I had these notes that I had made when I was studying mech. So it's just like a revision thingy. I just wrote down everything that I know about each of these topics. And yeah, now I'm just going to share them and show you what it contains. So the first topic that we have is forces and equilibrium, which is still the first topic even in today's um, mech syllabus. So within forces and equilibrium, the first thing that you need to note is that equilibrium means an object isn't moving. So, like this square thingy you can see here, it's not moving because the upward force and the downward force are equal. Similarly, if I add, let's say, a force that's pushing this to the right, let's say I make this 2 newtons, of course, and then I add a similar force here of 2 newtons. They balance out. So no overall force, which is no net force. So that's just one. No, that is the only condition actually for the object to be in equilibrium. So for objects in equilibrium, net force is zero, acceleration is zero. So how do we tackle this in like any normal question? Simple. We're supposed to find like usually in a mechanics question you would be given something like, let's say, if there's like a point here and there's a string attached to this point, you would have like some kind of object. Let's say this object is called object A, has a certain mass of m, and it's being pulled like this way, like that's the way the object is going. We have something that we call tension, which is created in the string that is holding the object. Now, the interesting thing about tension that helped me remember where these forces are acting, because like direction is really important with forces. The main, I'm sorry, I have a cold. The main thing that works with this is that the tension is always acting towards the point of like attachment. So this rope here, let me just highlight the rope a little bit. Oh, that's very I'm sorry. Okay, so let's highlight this rope. This rope is attached to this point right here. So the tension would be going towards this point. Tension is flowing this way. So that's why this would be our T force. And the force that's pulling this down could be any force. It could be an additional one, like someone pulling it, or it could just be gravity. Because if this were, let's say, like, if you just slant your head and look at it to think as if that, like, object A is going down, like if we're just hanging it, like a photo frame. When you hang a photo frame on the wall, gravity is like pulling it down, but the tension in the string towards the nail on which the frame is hanging, that tension is going to be equal to the weight that's pulling your photo down. That's how it stays balanced. It stays in equilibrium because both up and down forces are the same. That's essentially the principle behind everything we do in forces and equilibrium. So I'm just gonna show you how I solved this problem. Oh yeah, here. This is just a side note, right? Forces are vectors, so both have direction and magnitude. Sorry, so have both direction and magnitude. If a force to the right is positive, then a force to the left is negative. So here we're just going to assume that this whole thing is in equilibrium. Like a string is pulling an object, let's say that's like located here, into three different directions, but the object isn't moving. So how do you solve this kind of question? You need to resolve the forces. Resolving the forces means that you need to split it into its vertical and horizontal components. Because something like the T here, the T is simply put, it's like at a slant, right? It's not straight horizontally or vertically. It's straight, but it's like slanted at that 30-degree angle right here. So you need to resolve it, and you resolve it by finding the length. Like, you know how we do the Pythagoras theorem and the SOHCAHTOA for triangles? It's a very similar way that you resolve it here. So this would be your angle. This is the right angle. So that means that this is the opposite that we have here, right? So that means sine opposite. That is the so in the SOHCAHTOA. So yeah, because this is the hypotenuse. So this is the length which we're resolving. So the opposite, because it's opposite the angle, so this side would become t sine 30. You take sine of the angle when it's opposite the angle. So any um, length that is opposite the angle is just sine of it, basically. So t, because t would be the force in the string, sine of the angle. Then the other one automatically becomes cos. The other way to figure out cos is that cos has both of the right angle, and it also has the other angle that we're talking about. However, like on an inclined plane, which we'll talk about later, the way to determine sine is like super easy. But here too, it's pretty simple. So you resolve your forces. There's only really one force to resolve here because it's the only one at an angle. The other forces, such as this one, P here, then you have 16 here. These two forces are already vertical and horizontal, so you don't need to do anything special. So it says here, oh yeah, this is the note that I had. This, they never tell you this in any textbook, so this is very important to know, and it helped me a lot because I'm not a big physics person, but I was really good at math. So this is the one thing that is a lifesaver. And now we're going to make our upward equals downward and then left equals right. So when your upward equals downward, the only upward forces we have is the t cos 30. That's one upward force. So that's here, as you can see. And then we equate that to the downward force, which is 16. And using that, you can solve for t, right? So you get your t. And then you just equate t sine 30, which is the force at the going to the left, and you equate that to the force going to the right, which is p. And then you can solve for p because now you have your value for t. So you just input that and then you solve it. So it's pretty simple with that kind of question. Now, there's another thing that is kind of a big factor in a lot of these questions. Whenever you have a rough plane, or when you're told that the surface is rough, that means that friction is now into the equation. Friction has a formula where friction equals mu r. R is the normal contact force, and mu is the friction coefficient. So you use that to calculate friction. And over here we have our first object. So here we have a force F, that like capital F, the purple one, that's pulling the object towards the right. And then we have our friction, which is opposing. Friction is always an opposing force. So friction opposes that force. Friction's in green. So over here, because there's no other force that is actually pushing the object and it's in equilibrium, we're going to assume that all of the examples, they're all in equilibrium. So this is a rough horizontal plane. That means the capital F here is equal to this F since the object is in equilibrium. If the object was actually moving this way, that means capital F here is bigger than your friction. So you would have like that. It would be bigger than your friction. And we'll also look at questions on when the object is moving. But when you get like a normal forces question, you would get typical ones where it's in equilibrium. So don't worry about that. So yeah, that's it. And then your R would be here. It's the same R as this. These are the same things. So your normal contact force is like an upward force that acts on the object to cancel out the weight. That's how it always works. That's how it always exists. Normal contact force exists even without friction. However, if there is no friction, it means that there's no friction coefficient, right? Because if it's like not a rough plane and it's smooth, there's no friction. Even though in real life there is always friction, therefore the R is always present. But I'm saying theoretically because this comes in a lot of questions. So no friction coefficient, which is why there will be no friction. This is essentially becoming zero. However, this always exists. But 0 times anything is just 0. So yeah, that should be it for like a normal rough horizontal plane. Then this is the inclined one, where you would have mg sine theta here. This is special because mg is the mass of the object times gravity force. Sorry, force due to gravity, which is acceleration actually, which is always 10. Acceleration due to gravity in mechanics is always just 10. So I always make it like 10 m sine whatever the angle is. You always have to make it sine going down the plane. Sine is always down the plane. And sine is never up the plane. Like even if this force F was acting downwards, sine would like always be just down the plane. Okay. And then you would have the weight component cos that is acting downwards. The weight actually acts this way. The weight of the object, it acts like straight downwards. However, we resolve it into a horizontal force and a vertical force. So like those are the components of the weight. And you do need to remember where the cos and sine would be. I just remember where one of them is and I automatically know the other one is cos or sine. So yeah, this is how like I resolved it. Just to remember, you would see a diagram similar to this in your textbook. So this is just another tip. Component of weight down an inclined plane is always mg sine theta. And this is like super important. I just say down an inclined plane, mg sine theta, component of weight. It's like the one thing that you always have to remember. So these are the only two really scenarios that you would get with friction: inclined plane or horizontal. And with that, we come to the end of resolving forces in equilibrium in general. That's the end of that summary. Now I will move on to kinematics. Okay, so kinematics involves two distinct scenarios. The first one is where you have constant acceleration, and then the second one is where you don't have constant acceleration. So, for constant acceleration, we use something called the equations of motion. Usually, in your MF19, which is the formula sheet, you would get these three equations right here. And you typically use them in scenarios where you have two of the variables at the very least, because all of these three involve more than two variables. So you would need more than one. And yeah, you just need to identify what you are given in the question and what to use where. That's the main thing with these equations. U is your initial velocity, V is final, A is acceleration, S is displacement, and T is time. Now, I get that people from a physics background will definitely understand the difference between displacement and distance. However, I would just like to summarize again. Displacement is the shortest possible path taken from one point to another. Then you have distance, which can be as long as possible, but you would still get from that initial path, like you sorry, not the initial path, the initial point to the new one. So, for example, path A is longer. That's a longer distance than path B. However, they both have the same displacement since it's like, oh, they both covered that, like they both have that same, those two same points covered, if you get what I mean. The displacement is the same for the particle because it reached the same place regardless of the point, or sorry, regardless of the path it took. It reached the same place. Path A, however, has more distance. It doesn't have more displacement. Okay, now we're moving on to graphs. The very important thing with constant acceleration is that you will get, I think, three different types of graphs in questions. Sometimes I was even told to draw a graph. I've forgotten which one came in my exam, but uh, you do get like, I even forgot whether there was one in my exam, but you get these graphs. So basically, the first one is displacement time. Displacement on the x-axis, time on the y-axis. Sorry, the opposite. I'm so sorry. Displacement on the y-axis and then time on the x-axis. So displacement versus time. When okay, so you know the formula for speed. Speed. Oh my god. Speed, or maybe I should just call it like velocity rather. The formula for velocity is meters per second. Uh, Basically meters divided by second, which is what the I would say like gradient of this graph looks like. A gradient is always just y2 minus y1 over x2 minus x1. So the gradient of this graph would be velocity. Hence, if you have the gradient that looks like this smooth, plain line, it's just constant. It means that your velocity is constant and the object was just moving at the same speed. Um, I don't want to interchange speed and velocity too much, but that's what it is. At number three, the object is accelerating, which means that you can see the velocity going like down, coming up, it like a very sharp upward curve. And then over here at 4, the displacement is constant. Means that the object probably wasn't moving, right? So stationary. Because if it was moving, the displacement would be either going down, going up, but it's not. And 5, it says moving back to origin because the displacement is going down. Displacement is going down. If if I take like a path from, let's say, my kitchen to my living room, and then I go to the bathroom, then I go back to the kitchen, I'm back to where I started. So literally my displacement is 0. So this just shows like maybe the journey of an object to point of origin. If this is where it started at, then over here would probably be where it like is getting there. But essentially 0 displacement is when it means that object has come back. So it's at the origin at number 6 because displacement is 0. Then you have moving backwards from origin. So like I said, kitchen, living room, bathroom, back to kitchen. That's like number 6 here. Then let's say I go backwards to my garden. Now that would be the 7 here. But this is all like a constant negative velocity. Negative velocity means that we're just going backwards. Velocity is a vector. It has both magnitude and direction. So velocity towards the right, velocity towards the left, essentially. So yeah, the only tip I have for this is that the gradient of a displacement time graph is velocity. The value of that velocity, whether it's positive, whether it's negative, that just tells you where the object is going. Is it going backwards? Is it going forwards? However, that doesn't mean that negative speed does not exist, but negative velocity does exist. That's all I have to say. I forgot what I was going to say. Okay, second graph, velocity time graphs. Velocity time graph. So over here, I showed you the formula for velocity, which was meters per second. The formula for acceleration is meters per second square, which is derived from this form. That unit is meters per second square, derived from this formula, because we have the velocity here divided by time. So you essentially have like meters per second divided by another second. That's like meters per second square. That's the unit for acceleration. So the gradient of this graph is acceleration, and the area is displacement. These are the 2 key things that you need to be aware of. So an area above the 0 point here would be positive. Area below the 0 point here is negative. But yeah, 1 is your initial velocity. That's right here, because that's where your journey starts. 2 indicates constant acceleration, like the graph above, similarly. And then 3 would probably be like variable, which means that your acceleration is increasing or could be decreasing, but it's basically just changing. 4 means constant velocity. I mean, we can tell the velocity did not change at all during 4. 5 means decelerating. Decelerating, yeah, 5 would be decelerating because the velocity is going backwards. Velocity is going down. So that means that your speed or everything is coming down to 0 because that's where your velocity is going, right? So that is reducing your acceleration as well. Then you have instantaneously at rest, which means stationary for an instant, at number 6. It says instantaneous at rest because velocity is 0. Instantaneously means just like that, like within the snap of a finger. It's there, it's just stationary. And then 7 means speeding up but moving backwards. It's like walking backwards. You can be walking forward, slowing down, stopping, then walking backwards. That is exactly what this is. Slowing down but still moving backwards. Distance travel forward, distance travel backwards. The area, as I said earlier. Velocity time graph is pretty like simple enough to understand. Once you understand what this is like, why the gradient is velocity, you would understand why the gradient for this is acceleration, and the area is displacement. So Another tip, gradient of a velocity time graph is acceleration. Area under a velocity time graph gives it displacement. And these are some scenarios for when we use the equations of motion. So, an object is dropped from rest at a vertical height of 20 meters. Find the velocity of the object immediately when it reaches the ground. From rest here is key. From rest, oh, I'm sorry. From rest means that the object's initial velocity is 0. So we have u equals 0. That's what we can find from this question. The height is 20, so our displacement is 20. That's the displacement the object needs to travel. Acceleration is just acceleration due to gravity. There's no additional force that's going to push the object towards the ground except for gravity. Or maybe I should say pull. So here I've just drawn like a free form of what the object should look like. And we need to find v. So we need an equation that has all 4 of these variables because we don't know about time. So look for a formula which suits the variables, and this is the only one. So you substitute all your values, you find v to be 20 meters per second. And yeah, that's how you use your equations of motion. It's very simple. Sometimes, though, the only trick is with how the question involves itself with other topics. That's all I really have to say because that annoys me so much. Okay, second scenario, a ball is projected vertically upwards with an initial velocity of 5 meters per second. Find the maximum displacement. So over here, we know what the u is. The u is 5 meters per second. The final velocity. Okay, maximum displacement means that how high, let's say, the ball could go. That's what they're trying to tell us. Because if the ball is going up and then coming back down, that displacement is 0. But if we track the ball from the highest point at which it starts to bend to come down, that is going to be its highest height. So that's the maximum displacement that we're looking for. So when it reaches that highest point, it's going to go at rest for like, let's say, even a millisecond, but it will be at rest. Hence, you have a final velocity of 0. Acceleration would be -10 because we're going against gravity. So we're going up instead of down. Gravity is not coming down. In this case, this keeps happening. I apologize. So again, we have these, and we're going to use the same equation we did in the last question. And with this, you can substitute the values and then find your displacement. Okay, now we move on to non-constant acceleration. With non-constant acceleration, equations for acceleration, velocity, and displacement are given in the question. This is where we use differentiation and integration techniques from P1. So with this, we establish mathematical relationships. So this is what you need to remember, this relationship between acceleration, velocity, and then displacement. Acceleration is the rate of change of velocity, which is the rate of change of displacement. And rate of change is what differentiation is. You can tell acceleration is the rate of change because its formula is literally the change in velocity over time. That's its rate, right? Rate in the change. And then velocity is literally the same thing. Velocity is the change in displacement. So like you would have a final displacement, but I'm just going to put change in displacement over time. So yeah, that's the rate of change. And everything here is with respect to time. So you would have dv dt. You would, sorry, you would differentiate displacement to get your velocity equation. Then you would differentiate that to get your acceleration equation. Acceleration is like the final thing that you would get. They won't ask you to differentiate that, but you would be asked to, if you are given an equation for acceleration, let's say acceleration equals 2t in the question, then you would be asked to, let's say, integrate that to get your equation for velocity, then integrate that further to get your equation for displacement. And I know that with integration, we're going to have a constant c, but there's always enough information in the question to give you an idea of what the constant might be. Like they would give you the value of velocity at a certain time, and you can input those to get your constant c. Then you can use your equation to solve whatever you have to solve. So I think this is just an additional scenario or just like a note. If a question mentions total distance from t equals 0 to t equals any number, then equate velocity to 0 and figure out the values of t for which v equals 0. So by this, I mean that if a question tells you to find, let's say, total distance from time equals 0 to any time at all, then you would make velocity 0 and figure out the values of t for which v equals 0. If any of these values fall within the interval given by the question, break down the integration with limits. The reason for this is because the distance that your object is going to travel would probably, because distance is different from displacement, right? When you integrate your velocity equation, you're going to get the equation for displacement, not for distance. Displacement is going to give you the shortest, like, distance traveled, basically. It's not going to tell you, oh, like the object took a roundabout turn here, or the object took a circle to get back. Your displacement could be 0, but the object could have traveled a whole maze, which is why the total distance is important. So when you figure out the time t for which v is 0, it means that, let's say, like your initial velocity, like it's going this way, then it stops, so your v is 0 here, then it goes back this way. So that means v was 0 here and v was 0 here as well. Your velocity was 0 at both of these instances. Let's say this was at time 0 second to time 3 seconds, and then this would be at 3 seconds to, let's say, 5 seconds. But your displacement that it would show you when you integrate your velocity equation would just be this thing. However, however, the distance would be all of this. So you would be losing out on that. That's what this means. That's what this like tip is telling you. So yeah, you would just integrate with limits, like how you would do in normal calculus. And oh yes, please make sure that you have an absolute sign when you integrate, because you could get negative displacement. And yeah, that's like for I think, yeah, this is for non-constant acceleration. So we're done with kinematics. And the next topic now is Newton's laws of motion. Newton has 3 laws of motion, and this is essentially what this whole topic revolves around. Very redundant, according to me, but it introduces certain concepts that can be used to solve questions, and that actually unlock certain like problem solving methods in my head. So the first one here we have is an object at rest remains at rest, and an object in motion remains in motion at constant speed and in a straight line unless acted on by an unbalanced force. The reason I have this link to F equals ma is because F equals ma is just the second law. I know that there's probably a theoretical way of saying it, just like how there is for this one, but I really did not care at that time, and these are just summary notes. So F equals ma is the second law of motion. Acceleration and resultant force are always in the same direction. That's a very important thing to note, because when you have a question with, let's say, an inclined plane, right? And you have this, and let's say like there's a pulley here. Like there's a pulley. Sorry, I think, yeah. There's like a string attached to this point. Let's say it's pulling the object, right? Oh my god, wait. Yeah, the tension would be towards the pulley. My bad. So the tension here would be pulling the object here towards the pulley. And the we would obviously, resolve our forces. We have the component of the weight that acts down here, let's say sine theta. We don't know the angle. And then we're being told that, oh, the object is actually moving towards the pulley, which means that acceleration is this way. And it also means that the resultant force is also in the same way that acceleration would be. And that's all proven through like the formula. Because if your acceleration is positive, then, oh my god, if your acceleration is positive here, your resultant force is also positive, because mass is the only thing here that can never be negative. Acceleration is always going to be either positive or negative, which causes your overall force to be negative or positive. And that's a big indication to tell you where the object is going, if you know where your resultant force is going. Okay, the third law states that for every action in nature, there is an equal and opposite reaction. Right. Oh, this is the momentum topic. Okay. Oh no, never mind. Momentum is a separate topic. Connected particles. Yeah, like I was talking about with the pulley. I'll do like a whole worksheet on pulleys, because I really enjoy solving questions of this nature. They come in heavy amount of marks. I saw a question which was 8 marks. When I solved it, I got like 6 out of the allocated 8, because I forgot that the string breaks in said question. And in my head, I was so annoyed with the string. But yeah. So connected particles, the pulley can either be like this, or it can be an inclined one. Or the inclined plane, but 2 different. So you could get 2 whole different angles here. I've seen all of these, so I just had to put them in these scenarios. These are completely different things. These are like when one is a driving force and one is another thing. It's a whole different scenario. So the first one, you have a pulley, and with the pulley you have like just one same string. So 2 blocks are attached, different masses. If the block is moving sorry, if the block is moving down, its weight overcomes the tension. Hence, weight is bigger than tension, so resultant force, which is F equals ma, would be weight minus tension. Because your resultant force is moving down, but to solve for resultant force F, the tension here needs to be smaller than this weight in order for F to go down. So you would have weight minus T equals your F, correct? So I just substituted that into F equals ma, and that's how I got W minus T equals ma. And then if your block is moving up, weight is less than tension. So tension is pulling it upwards. Hence T minus W equals ma. Your resultant force equals to mass times acceleration. And we can always use a combination of these two equations, because when we get a pulley question, one is always going to go down, one object, and then the other one is going to go up. So you can form two different equations, then you can use those two different equations to solve for your tension and acceleration, which is a general demand in, I see, almost every other paper or every paper. So the only different thing about both blocks is that they have different weights. Acceleration and tension are the same because they are connected by the same string. And really, that's all that you need to know about this. Every question you get will be fairly simple enough. Now, second scenario of where one string connects two different weighted objects, you would have an inclined plane. Instead of, let's say, object A hanging as object B is, same thing. So the same principle as above would definitely apply to B for if the block is going up, if the block is going down. For A, if the block is like sliding up, like A is going up, that means that the tension is overcoming the component of the weight that is pulling the block down. So T would be greater than the force pulling the, oh my gosh, T would be greater than the force pulling the object down for A to go up. Now, it depends on whether your plane is smooth or not. I assume that the plane would be rough, so I did add my friction to this. Friction always acts opposing the motion. And then for A to be sliding down, actually friction needs to be, oh yeah, friction would be here. So when A is going down, the only downward force that would overcome tension would be the mg sine theta. However, if the A is going down, it means friction is acting this way. If A is going up, friction is acting that way. We need to keep that in mind, because friction is always opposing motion, essentially. And yeah, based on that, you can get your equations. And this is just the same thing, but this time, both of them have both of them have the inclination. So you would just do this same type of equation, but for both blocks, depending on whether or not friction exists. So yes, that is connected particles for that kind of scenario where they're both connected by a string. So yeah. Now, this is a scenario in which connected particles, one of them is pulling the other one. You could say that in this one of them is pulling the other, but that's only because of the weight. In this one, there's like an additional force created by, let's say, an engine, by a car, that's like pulling a load behind it. However, the load and the car are connected. So here, the truck pulls the cart, and F is supplied from, I need to say, the truck's engine here. This is mostly done in work, energy, and power, so I'm just like showing you that this is also connected particles. However, we do not look at it in here. We look at this scenario in work, energy, and power. And the same thing could be done on an inclined plane. Okay. So, the fourth topic that we're going to deal with today is momentum. The main law of conservation of momentum is what this whole topic revolves around. Momentum before collision and momentum after collision are equal, which is your law of conservation of momentum. So, the formula for momentum momentum is represented by a p here, like a small p, because you also have mass in the equation. So momentum equals mass times velocity. So this is just how to calculate momentum before collision. So these two objects, A and B, haven't collided yet. However, A is moving towards B with this velocity. So before collision, its momentum would be like you would calculate the momentum overall for the entire system. So you have MA/UA plus MB/UB. And since B has a velocity of 0, it's basically just 2 times 5 here. So we would have 10, which is the momentum before collision, is equal to the momentum after, which is represented by 5 times VA plus 3. Because this is just an example I took out of a textbook. So after collision, we don't know what the velocity for A is, but velocity for B is said to be 1. But the mass stays the same. So we can find the velocity of A after by just by using your normal algebraic rules and then solving the equation. And I got it to be 1.4 meters per second. And a note to be taken, kinetic energy is not always conserved, but momentum is always conserved. The reason I say this is because a lot of people tend to think that kinetic energy will always be the same after and before, but that's not true, because energy always gets converted to other forms such as heat. It can get lost to the surroundings. Not lost, but like converted essentially. So I use the same scenario as above, the same example. So kinetic energy before collision is 10 joules, and then kinetic energy after collision is 6.4. So we've lost 3.6 joules to the environment, let's say as heat or sound. This is just another collision. This is when the two objects coalesce, whatever you want to call it. They stick together as one after the collision. In that case, both of them would have the same velocity because they're traveling as one object now, not two distinct ones. But yeah, over here you do need to add the masses separately in a bracket. However, their velocity is going to be the same. So just take note of that. And you solve it as normal. What I got here was 3.43 meters per second per second. And that's just it for momentum basically. Note here, when two bodies move in opposite directions, this should be like after collision. When they move in opposite directions, the velocity of one is positive and the other body is negative. So like here, these two objects, first of all, this one isn't really moving. Or we don't know, actually. We don't know whether it's moving or not. But after collision, both of them have a velocity of 0. So what really happened? So over here, because both of these have a velocity of like 0, essentially momentum after is just 0. So here the initial momentum, when you calculate it, first one is 4, second one is 3u. So that means that u is negative. So B was actually moving in this direction. because we assume 2 to be positive here, because this is a positive value. So if you assume your right direction to be positive, that means negative is left. And that's essentially what I said. Now, the very last topic of mechanics, and then we're done with the syllabus, is energy, work, and power. So, the first thing that you actually look at is work done in any textbook for this. Work done by an object in motion is the product of the force and the distance moved parallel to that force. So in this scenario, this shaded block here is moving 10 newtons to the right. So if the block moves 10 meters, the work done is 10 by 10, which is 100 joules. So over here, the force that is pulling the object or doing work on it is 10 newtons, but at an incline. So you need to resolve the force over here, right? So this is the opposite of the angle, right? So that would be sine 10 sine 45, but over here you get 10 cos 45. There is no, like, the object doesn't move upwards, the block is just moving 10 meters. So 10 meters to the right because there's no force opposing it at the left. So the work done would be 10 cos 45, the force moving it to the right, times the distance. And that gives, oh, I didn't expand, but that gave me 50 root 2 as my value. And then the last example, in this case, the block doesn't move due to no force parallel to the floor. You need to keep in mind that work done is only done when the object moves parallel to the force that moved it. So if the object moves, let's say, upward, and the force is moving it upwards, but there's also forces going left and right, however, it did not move that way, then the left and right forces are not counted into your equation. It's only the up one since the object moved up, if that makes sense. Next thing we're going to look at is energy. Kinetic energy arises due to the motion of a particle at its speed. So from physics, this formula is just kinetic energy equals half times mass times velocity squared. Potential energy arises due to the position of an object under gravity. So potential energy equals mass times acceleration due to gravity times height. In a situation where there is a smooth plane and both kinetic energy and potential energy are involved, potential energy loss equals kinetic energy gain. Because this is a smooth plane, so no friction, and you know that friction generates heat. So if there's no friction, it means that no energy was lost as heat. So it's a perfect system. And your PE loss would be your KE gain. If there is friction, it will not be the same. So you can just equate the two things. Your masses would automatically cancel out. And then you can rearrange this to get whatever you want. Height, velocity. Essentially, this is just an equation that relates velocity to height, because your acceleration due to gravity in mechanics is always an assigned value of 10. So that's for that. Now we have the work energy principle. This is a very short topic, but it's used in, I think, just one question. Mechanics has 7 questions in total, and a lot of the questions incorporate 2 or 3 different topics. But work and energy can come in another topic, or it can just be like its own question. So the work energy principle, this is one formula that you would probably be using more than others. So work done by driving force minus work done against resistive forces. Driving force is the resultant force. The sorry. Over here I made a note that resultant force is 0 if object is sliding slash moving without external force. That is from rest. Um, because there is no like driving force, right? The external force is your driving force. And resistive forces are 0 if your plane is smooth. Resistive force is any force that opposes motion. So we're just talking about friction here. But if there's any other resistive force in the question, they just tell you resistive forces. And that is equal to the gain in potential energy plus the gain in kinetic energy. Kinetic energy could also be a loss since your okay, actually it won't be. Velocity in the kinetic energy equation is squared. So it doesn't matter if the object's moving in the opposite direction. It would be like a negative value squared, which is positive. Just remember that kinetic energy can never be negative. Any energy value is not going to be negative. So over here, your gain in potential energy, oh my gosh, is 0 if motion is in a straight line. Why is that? Because motion in a straight line means that the object is not moving up or down. Then gain in kinetic energy is 0 if the object has constant speed because velocity is not changing. So that's just like an explanation for this. I'll show you how to use this when I'm doing more of the worksheet examples. This is just a summary of the topics in the syllabus. Power. Power is actually just the product of the driving force, which you can get from this formula up here, times your velocity. Or power is work done over time. So when velocity is constant, resistive force equals driving force. Because when velocity is constant, acceleration is 0. Since acceleration is change in velocity, velocity being constant means no change in velocity. So acceleration means 0 means resultant force is 0. So that means that object is in equilibrium because there's no net force, right? It's not moving, no acceleration, or it's just moving in a constant motion. That means that the friction or whatever resistive force you have is the same as the force that is moving the object forward. And that is all that you need to know for mechanics for your syllabus. This is from the 2024 syllabus, which is the exam that I wrote, but it also applies to the year now and up 2026, and it applies to 2027 as well. And that is just it. We're done with the syllabus in under an hour, a summary. I hope this is a good refresher for everyone that's going to take the exam. And if I miss something, please do let me know. I will do the worksheets and everything and then solve like the most difficult questions for each of these topics. I'll like compile all of them personally. Thank you guys for watching. Leave a like if you liked it. Thank you.